Wow, hello guys, welcome to my channel. Welcome to Master Builders Online Academy. I want to sincerely appreciate every one of you who have taken out time to always come over here to this dashboard to watch our content and then learn from this platform. Thank you very much for being part of this great body. Thank you for subscribing and then for watching our content, even giving us positive comments and then liking our videos, more also sharing the videos. So in today's lesson, I'll be showing you some basic things in strength of materials. Okay, so we'll be looking at resolution of forces and then we'll be looking at bending stresses as we will have it in this module. But meanwhile, one of the things that you must do is that pay maximum attention so that you will be able to understand every basic conditions that I will be unveiling while I teach. All right, so understand that everything that we do on this platform, we are always law abiding. As such, we embrace principles that much. So please ensure that as I teach, seek to understand the principles, not exactly how this problem is solved, because every problem like this will always require you use the same principle I use now to solve as many problems that you will have under these particular areas I will be touching in this video. So guys, without further ado, let's dive into solving these problems. All right, so the very first question that we have here now, guys, is that we should determine the resultant force in size and direction of thrust of 7 kilonewton and a pull of 5 kilonewton acting on a peg as shown below. So as you can see, the diagram is already given to us. So the one that is taken as pull is the one leaving the joint, while the one taken as thrust is the one entering the joint, which is 7 kilonewton. And as you can see, between the horizontal line and 7 kilonewton, the angle of inclination is 30 degrees. And between 7 kilonewton and then 5 kilonewton, we have the angle between the two forces as 15 kilonewton. That means from the horizontal to 5 kilonewton will actually be the sum of 30 and 15, which will give us 45 kilonewton. It shows that this angle between the horizontal axis and 5 kilonewton is 45, right? So we can put this here from here to this point. That's what we are talking about now. The angle here is now 45 degrees. So as you can see now, in order to solve this problem, there are so many methods that can be applied to solve this problem. You can use parallelogram law of vector to solve this problem for as long as we have only two forces, okay, and then the angle between them is known. Then you can also use resolution of forces to solve this, okay. So in this video, I'll be showing you exactly how to use resolution of forces to solve this particular question. Then in subsequent videos, I will also show you how to use the parallelogram law of vector or forces to also solve a similar problem like this, if not this particular question. Okay, so let's dive into this problem as we begin to unveil the basic solution to this. Remember, whenever you are asked to find the resultant, we are actually looking for that one singular force that can represent these two forces that are given. We are looking for one singular force that can represent two forces that are given like we have in this case. So if this is known, and I have mentioned now we are using the resolution of forces, so we can quickly draw the free body diagram of this sketch. Now let's have this. So let's take, for instance, we have x and y axis drawn, okay. Then we have, if you look at the first force, you will find out that which is 55 kilonewton is on the first quadrant, right? So we can just take something like this. Let's assume we change the color of this guy to black because this is the actual force at 45. Remember, from x axis to 5 kilonewton is 45, so we'll put this here, and then we can just put this guy. All right. So this is the 5 kilonewton, and then the angle it makes with the horizontal is now 45 kilonewton. Are you there? Now again, when we check the next one, which is 7 kilonewton, you will find out that this 7 kilonewton will be coming out from the third quadrant. If you see the direction, as you can see now, as you can see from here, the direction, it will come out from the third quadrant, and this is the third quadrant here, as you can see in our new diagram, right? So all we need to do now is to allow this guy comes out from the third quadrant. Why? Remember that under the characteristics or properties of forces, we were told that force have what we call the line of action. So a force in one quadrant can actually be extended to come out from another quadrant. So if we do this, because this 5 kilonewton is making angle 30 with the horizontal, so we are going to also do that in the third quadrant. So let's get our shape. Now from the third quadrant, we have this making angle 30 with, then we put our 7 kilonewton here. That's good. So to the horizontal, as you can see here, the angle between 7 kilonewton and the horizontal axis is 30. So we can put this like this here. So we have 30 kilonewton. Now remember that this is our y-axis, and then this is x-axis, as you can see. Okay. So now in resolving these forces, you need to understand that when resolving forces along x-axis, most often the time you make use of cos theta, and some other time you use sin theta. If you check some textbook, why do we have to switch this? One of the basic things you should understand is that whenever the angle is between the force and x-axis, when you are resolving along x-axis, you use cos theta, and when the angle is between y-axis and the law force, then when you are resolving along s-axis, you use sin theta. This is the interswitch. Okay, so one of the things now is that let's resolve these forces, as we can see. So sum of fx is equal to, we can call this is equal to f1, then equal to. So as we resolve these forces to x direction, you also need to understand the basis of quadrant. All right, so now that we have f1, as you resolve along x-axis, any force in the first quadrant will be taken as what? Positive for x. So this becomes 5 cos 45 degrees. Now, when you have your force on the third quadrant and then resolve along s-axis, you have a negative sign, then minus 7 cos 30 degrees. I hope you are following me. And then when this is done, when you impute this in your calculator, you will have minus 2.53 kilonewton. We have resolved this force to x-axis. Again, we want to quickly resolve the same force to y-axis. And in resolving this to y-axis, again, we have sum of fy is equal to, let's take this as f2, and then this will be what? 5 sine 45 degrees. Now, for this other guy, which is resolving along y-axis, any force on the third quadrant will also be taken as negative when you are resolving along y-axis. So this becomes 7 sine 30 degrees. Then the answer to this is 0.04 kilonewton. So we have been able to resolve these two forces along x-axis and then along y-axis. All we need to do now is to draw the new sketch for this system. But meanwhile, you understand that f1 is negative value, which is negative of x, and fy is what? Positive. That means this force is on the second quadrant. So let's have our shape. Second quadrant. All right. Okay, so this is second quadrant, as you can see, right? So this is our f1. and then this is our F2. So now the resultant force is the force that will come out in between these two forces. Are you there? The force that will come out in between these two forces. So what is that force? Now we'll now take it out in between the two forces. We can also use our shape. All right, let's use our shape. So in this case now, this is our resultant force. Our resultant force, R. So now we already understand that we have this sketch to this direction because F1 is negative and y F2 is positive. Having gotten to this level, all you just need to do now is to get your resultant force. So you can get this out, and then you have an angle here, angle theta, right? So this resultant force that we have here, or let's take for instance this angle alpha. All right, so this is the angle of inclination of the resultant force to the horizontal axis. Now this is what we have, guys. Now the question is, listen carefully, the question now is we have to find the resultant. So as you can see now, we can actually use Pythagoras theory to find our resultant. So resultant force in magnitude is equal to the square root of F1 squared plus F2 squared. So R becomes the square root of F1, as you can see from here, is minus 2.53. So put the value there, minus 2.53 all squared, then plus 0.04 all squared. And then when we find this, R becomes the square root of 6.4025. If you then find the square root of 6.4025, we then have our answer to be 2.53 kilonewton. So guys, the resultant force of this particular system is 2.53 kilonewton. But remember, the question did ask us to determine the resultant force in size, which we have obtained, and direction of the trucks. And direction, are we there? And direction. So how do we find the direction now? All right, so we need to obtain alpha. In order to obtain alpha, we can put it now. Direction. Okay, let's say the direction is theta. So the first thing we will find is alpha, which is the angle between the resultant force and the horizontal axis. And to find this, we'll simply use tan alpha. Remember, it is alpha that we have in this diagram, right? So it is alpha that we have there. It's equal to tan inverse is equals to sum of Fy over sum of Fx, which in this note, we have this as F2 over F1, all right? Now, by the time we make alpha the subject of formula, we'll have that alpha is equal to tan inverse of F2 over F1. So all we just need to do now is to put in the value tan inverse of 0.04 all over 2.53. Are you there? All right, so if we divide this and then find the tan inverse of this result, our alpha becomes 0.9057 degrees. We can actually take alpha as 1 degrees. Okay, let's take alpha as 1 degree. So 0.1 degrees. This is our alpha, approximate value. Okay, so that means to the horizontal, the resultant is 1, but the direction of the resultant is either in whole cycle bearing or in quadrata. So if it is in whole cycle bearing, since the resultant is in second quadrant, to find the direction of the resultant in whole cycle bearing, we will remove alpha from 180. Why? Now, assuming we come to this diagram, follow me up. Okay, so this is the diagram. If I extend this line here, as you can see, from here to where we meet this line is the theta we have there. So that means the sum of theta and alpha will give us 180. Remember that theta is what we used as the resultant, as the angle or the direction of the resultant, right? So all we need to do now is to say that theta plus alpha is equal to 180. Why? Sum of angles on a straight line. So we have theta plus alpha is equal to 180 degrees. So theta is equal to 180 degrees minus alpha. Then we have 180 degrees minus 01 degrees, and then we have 179 degrees. This is the direction of the resultant force. This is the value, and then in whole cycle bearing. But take for instance, we want to find this value in quadrilateral bearing. What are we going to do? We just need to acknowledge the quadrant in which we have our resultant, and then this quadrant is quadrant, second quadrant, quadrant 2, right? And in this second quadrant we have, and the angle must be between the resultant and y-axis. But the angle we obtain is between the resultant and x-axis. So that means the angle we have with respect to x-axis, we will remove it from 90. Remember that quadrilateral angle, the sum of angle in a quadrant is 90. So when we remove alpha from 90, we'll be able to get the angle the resultant made with the y-axis. This is clear, right? So we have this theta in quadrilateral bearing is equal to 0 into 90 minus alpha west, and then we have 0 into 90 minus 01 degrees west, and then this will give us 89 degree of west. This is the angle we have. So therefore the resultant is equal to 2.53 kilonewton, and the direction is equal to 89 degree west, 179 degrees in whole cycle. So this is the resultant, and then the direction of the resultant as far as this question is concerned. So guys, I wish you all the best. It's very, very simple. All you just need to do is to resolve to the x-axis and then resolve to the y-axis. Very quickly, let me blow up your mind again with another question that we have right before us right now. Okay, so let's dive into that question. Okay guys, now we have another question before us, and then the question is this: a 2-meter long steel, that means length, steel beam 30 mm by 30 mm in cross section is simply supported at each end. Simply supported at each end. That means we need to draw a free body diagram for a simply supported beam. All right. Suppose it fails when a load 10 kilonewton load is applied. Remember, 10 kilonewton is a point load. We are asked to determine the equivalent uniformly distributed load that will break a cantilever beam of the same material, 50 mm wide, 100 mm deep, and then 2.5 meter long. So guys, as you can see from this question, we have two types of beam here, and then we are comparing one to another. So the first type of beam mentioned here is a simply supported beam, and then this simply supported beam is to support a point load of 10 kilonewton. All right, so we will take the simply supported beam and then bring out the properties. Now let's say for the simply supported beam. Now for simply, this is the nature of simply supported beam. All right, so this is the free body diagram. Then we have a load of 10 kilonewton, and then as you can see, the span of this guy is 2 meters. Okay, please just make sure you're following as you can see on the screen. All right, so other parameters that we're given is that this beam is of a section 30 mm by 30 mm. I hope you can see this 30 mm by 30 mm. What does it mean? It means that the width is equal to 30 mm. And then one of the things you must do is that we can either convert to meters or solve in millimeters, but let's go ahead and convert to meters. So this, to convert in millimeter to meter, you divide by 1000. This will give us 0.03 now in meters. Then the depth is equally 30 millimeters. And if we do the same thing, we divide by 1000, we have 0.03 meters. So the parameters for us to be able to get the area of this section or whatever geometric properties of this section are already in place. Are you there? This now is that then from the question we're given now that the point load is 10 kilonewton. And then to solve with this, we have 10 times 10 raised to the power of 3 Newton. Remember that kilo means 10 raised to the power of 3. So we just remove the kilo. Now, what next? The next thing we are quickly going to do now is to find the section modulus. Okay? All right. As you can see, if it is elastic, all right. So we're using the elastic section modulus to have this done. So elastic section modulus is given as B D squared over 6. And then we have our B to be 0.03 multiplied by 0.03 raised to the power of 2 all over 6. And then when we solve this, we find out that Z is equal to 4.5 times 10 raised to the power of negative 6 meter raised to the power of 3. So we have obtained the value of Z. Then again, we need to find moment. Now, one of the things is that you need to recall that the maximum bending moment for a simply supported beam carrying a point load at the midspan is given as PL over 4. Then if we find this, moment becomes 10 times 10 raised to the power of 3 multiplied by the span is 2 meters all over 4. Are we there? So as we move down, we'll find out that the moment is equal to 5 times 10 raised to the power of 3 Newton meter. All right, so we have gotten moment. Guys, we are done. Then all we just need to obtain now next is to find the stress. One of the things you must understand why we are doing all of these things is that as far as this question is concerned, we are told that if the beam have the same material or they are made of the same material, they have the same material properties, right? So because they have the same material property, that means the stress induced in this cantilever beam is the same stress induced in the simply supported beam. So what is common between them is the stress. So we need to find stress for this. Now we also understand that the bending stress is given as the maximum bending moment divided by section modulus. This is the stress. Okay, and then we call it the maximum stress. All right, since we have maximum bending moment, this is the maximum stress as well. Then this will be equal to 5 multiplied by 10 raised to the power of 3. Remember that this is our moment. All over section modulus is 4.5 multiplied by 10 raised to the power of negative 6. And then this is now equal to, if we multiply this and then divide out, the result becomes 1.11 times 10 raised to the power of 9 Newton per meter squared. This is the stress induced. Now, everything that we need to do as far as the simply supported beam is concerned, we have done it. The same procedure we went through in solving for simply supported beam is the same procedure we are going to go through again now to solve for the cantilever. So we are going to take the cantilever. Now, remember that the cantilever also have its own properties. It has the section, depth, and width. It has the length. So let's quickly go down and then have 4. The cantilever beam, we'll draw a cantilever. A cantilever is a beam that is fixed at one end and is free at the other end. So this is a cantilever beam, and then we're told that the span is 2.5 meters. All right, please check up here, you see it here, and 2.5 meter long. That's the property of the cantilever. Okay, and then remember again that this cantilever is to carry a distributed load, UDL, and in this case distributed load is given as small letter W in kilonewton per meter. Are you there? So now, what is the section property for this? The section property were given 50 by 100. All right, so this is 50 mm, and then this is 100 mm. Okay. Now, again, in this case, we are given that B is equal to 50 in millimeters, and by the time we convert to meter, we have 0.05 meters. Already you know how to convert from millimeters to meters. If you don't know, simply divide the given value in millimeters by 1000, and then you have it in meters. Then D, which is the depth, is given as what? 100 millimeters. Okay, so to convert 100 millimeters to meter, divide by 1000, again you have 0.1 meters. So we have been able to get the depth of this section. Again, the load is what we are looking for, which is the UDL. Okay, this is the load that we are looking for, unknown. So this is what we have to calculate for. So one of the things that you just need to do now is that you still need to calculate for section modulus for this material, then calculate for the moment, and then calculate for the bending stress. All right, so let's start with the section modulus. The section modulus Z is equal to BD squared over 6, and then this will give us 0.05 multiplied by 0.1 squared all over 6. Then we will have the value of this guy as 8.33 multiplied by 10 raised to the power of -5 meter raised to the power of 3. So we have gotten the section modulus. Again, we need to get the maximum bending moment for this simply supported beam. So the maximum bending moment for a cantilever carrying a UDL is WS squared over 2. This is the maximum bending moment for a cantilever beam carrying uniformly distributed load. All right, so we were given the span, so this becomes 2W multiplied by the span is 2.5 squared all over 2, and then when we solve this further, we'll have this as 3.125 W. This is the moment. Again, after getting this, we now get the maximum bending stress. Maximum bending stress. Okay, so the maximum bending stress is also maximum bending moment all over section modulus. I hope you are following me now. All right, so in this case, remember that we were told that these materials, they have the same property. As you can see, the simply supported beam and the cantilever, they have the same materials. So because they have the same material, all you just need to do now is to equate their stresses. What it means now is that this stress, as you can see it here now, is the same as the one we have already obtained. This one you can see here is the same as the one we have already obtained. So what we just need to do is to substitute the stress we had before here. And that stress, if you come up here, you will find out that that stress is 1.11 multiplied by 10 raised to the power of 9. Okay, so we'll come here and do that substitution. This is 1.11 multiplied by 10 raised to the power of 9, which is equal to the moment we just obtained for the cantilever is 3.125 W all over the section modulus, as you can see here, is 8.33 multiplied by 10 raised to the power of -5. So 8.33 multiplied by 10 raised to the power of -5. This is it. So as you can see from this expression that we have here now, if we say this is all over 1, we have only W as the unknown. So all we just need to do is to find a way to make W the surrogate of formula. Haven't done that, then we are good to go. It's as simple as this. So we just simply say here that. So what we do now is to cross multiply. As we cross multiply from here, we'll have this as 3.125W multiplied by 1 is equal to 1.11 times 10 raised to the power of 9 multiplied by 8.33 multiplied by 10 raised to the power of -5. I hope you are here. So this will still give us 3.125W. Anything multiplied by 1 gives you the same thing. And then when we multiply this outcome, this will give us 92463. You can check it out. So when you multiply 1.11 times 10 raised to the power of 9 by 8.33 times 10 raised to the power of -5, we'll have 92463. All we need to do now is to make W the subject of formula, and if we do that, W is equal to 92463 all over 3.125. Are you there? Now, if we divide this, guys, as you can see, this will give us 29.588 times 10 raised to the power of 3 Newton per meter. Okay, guys, so in kilonewton, we can approximate this to be what? 30 multiplied by 10 raised to the power of 3 Newton per meter. And then if we have to leave our answer in kilonewton, we have that W is equal to 30 kilonewton per meter. This is the distributed load that we'll have for this simply supported beam. Don't forget that we were actually asked to calculate the uniformly distributed load, which is the one you can see here on red. Are you seeing it? As you can see now, so this is it. This is what we are asked to look out for, the one on with color. So, all right, so this is it. This is it. All right, so we have been able to obtain this. So guys, anytime you are given a question like this, your interest is to first solve for the simply supported beam, then solve for the cantilever. But when the materials are the same, it shows that their stress is the same, the strain is the same. So they have the same material property. So any of the material property that you are able to get access to with the given parameters will serve for both cases. So take for instance, we are given UDL for the simply supported beam. The same thing we have done now is what you're going to do, only that for simply supported beam, the maximum bending moment will now become WS squared all over 8. So first you get your section modulus, followed by maximum bending moment, followed by maximum stress for the one whose load is known, and after which you move to simply the cantilever beam, and then for the cantilever you draw, bring out the parameters, again you find the section modulus, after which you find the maximum bending moment, then find the stress. Because the materials are the same, the stress are the same, and then all we just need to do is to equate and then substitute our values. After doing all of this, we make W the surrogate formula. This is the UDL that we are asked to calculate. So guys, thank you for watching. We love you so much. Thank you, thank you, thank you. In the next module, I'll be teaching you another aspect in strength of materials. Make sure you share this video, make sure you like this video, and make sure you leave a comment at the comment section below. Thank you very much. We love you. See you guys in the very next class.